Okay, so in this situation, we have two eagles moving at right angles to each other and colliding. So they're going to collide at an angle. In these sorts of situations, we still have momentum conservation, but we have to keep in mind that, momentum is a vector quantity. It has a direction, so we're going to have to account for that when we look at this scenario. So I'm going to draw a simple picture of what's going on. So if we have, and I'm just going to draw the eagle as a circle just to keep it easy. We have eagle 1 moving at, or with a mass of 4.3 kilograms, moving at 7.8 meters per second. And we have the other eagle, its mass is 5.6 kilograms, and it's moving at 10.2 meters per second. At a right angle, so we can see this. It doesn't say what direction, but we know that they're perpendicular to each other. So before the collision, this is what's going to happen. This is what's happening. Now, without really knowing a whole lot about physics, I think we could understand the idea that when they collide and stick together, that they're going to move off at an angle in this direction to some extent. All right, and if you think about why that is, it's because of momentum conservation. We know that the first eagle has momentum to the right, and the second eagle has momentum in the upward direction. So the total momentum of the system here is up and to the right. So after the collision, we would expect them to move up and to the right. They're not going to move, leftward or downward. That wouldn't make any sense in this scenario. Okay, so afterwards, we expect that these two eagles combined, that their combined mass would be, 9.9 kilograms, would be moving off at an angle in some direction this way. Okay, so the way I'm going to set this up is I need to keep a separate account for the x direction and the y direction. So I'm going to write that like this. In the x direction, I have the first eagle is in motion in the x direction, but the second eagle has no velocity in the x direction. After the collision, they stick together and they move off with some velocity in the x direction. I'm going to call that Vx prime. In the y direction, the first eagle has no momentum. It's not moving in the x direction. The second eagle definitely does. And then afterwards, they stick together and move off with some velocity in the y direction. So I can find the x velocity and find the y velocity, and then use that to find the overall velocity, which is, v prime that I have here. Okay, so to solve for Vx prime, I'm going to have m1v1 over the total mass, and Vy prime is going to be m2v2 over the total mass. So we can find those values. What we have for eagle 1, we had 4.3 kilograms times 7.8 meters per second. And we're going to divide that by the total mass, which was 9.9 kilograms. And I get 3.39 meters per second in the x direction. And here, M2V2 is going to be 5.6 times 10.2, and I'm going to divide that by 9.9. I get 5.77 meters per second. So first thing to notice, and let's tie this back in conceptually and make good sense of it, notice that the x velocity here is smaller than the y velocity. Think about why that makes sense. If we look at this situation, the heavier eagle is moving faster, so there's more momentum in the y direction than there is in the x direction before the collision. So I would expect that they're going to move more in the direction of this eagle than the other one. And that's what the results show us. So what we have overall is we have an eagle, a combination of two eagles that are moving at 3.39 meters per second in the x direction and 5.77 meters per second in the y direction. So their overall velocity is going to be in this direction, which is more upward than rightward. I can use the Pythagorean theorem, since these are perpendicular, to find the overall velocity. So 3.39 squared plus 5.77 squared, and take the square root of that. I get 6.69. So that's how fast they're going after the collision. I also want to know the direction, so I'm going to find this angle theta. I know that the angle is going to be the inverse tangent of the opposite side over the adjacent side. So if I were to do that, I got 5.77 divided by 3.39, and I take the inverse tangent of that. And that comes out to be 59.6 degrees. So they're moving up and to the right at 59.6 degrees. If these were cardinal directions, I would say that it's 59.6 degrees north of east in that case. All right, so it's important that we understand that momentum is a vector, so we want to look at the x direction and the y direction separately from each other and understand the momentum there, but also understand that the momentum is conserved in each direction, the x direction, the y direction, if we were looking at a 3D situation, in the z direction as well. I think we understand conceptually why these eagles have to move up and to the right, and why ultimately they're moving more upwards than rightwards in this case. So, just qualitatively we can understand that, and then the mathematics that we used here supports that idea.